Today's example is about determining if a reaction is spontaneous. Okay, so remember, if a reaction is spontaneous, that means it will happen without any external input. Okay, and to do that, what we're going to do is calculate this delta G naught of the reaction. So the reaction we're looking at is methane, so CH3 carbon tetrahydride gas plus 8 oxygen gas goes to CO2 gas plus 2 H2O and 4 ozone. Okay, so this is the reaction we're looking at. And in order to determine if it's spontaneous, we are going to calculate this delta G naught of the reaction. Okay, so remember, this is just kind of a symbol to let us know what we're looking at. So the delta means change. So this is the change of the process that happens between the reactants and the products. This G stands for Gibbs free energy. And this value tells us whether things are spontaneous or not spontaneous, taking into consideration all the different thermodynamic properties. So delta H, delta S, and also temperature. And so if you have a delta G value that's negative, that tells us that the reaction is spontaneous. If you have a Gibbs free energy change that's positive, that means the reaction is non-spontaneous. Okay, so spontaneous means the reaction will happen without any external input. Positive, non-spontaneous means that the reaction needs some kind of external input. Okay, going back to this little symbol, this naught thing means standard conditions or standard state. And that's 25 degrees Celsius and 1 atm. Okay, and then this last little thing, RXN, is a shorthand for reaction. We just throw that on there to say, hey, this is the delta G value for the whole entire reaction. Okay, so is this reaction spontaneous? We're going to determine if this delta G of the reaction is a positive number or a negative number. That will tell us if it's spontaneous. Now, there's 3 different ways to calculate delta G. Okay, the first way is this delta G equals delta H minus T delta S. And so notice this way right here doesn't have that little naught symbol. So that means we can calculate delta G at any temperature conditions. So this T in the formula represents temperature in Kelvin. And if we know the temperature, then we'll be able to calculate the delta G at that temperature. Okay, and if we're looking at standard conditions, then we put in 25 degrees Celsius converted to Kelvin, and it will give us the delta G at standard state. Okay, remember our delta H value is enthalpy, and our delta S value is entropy or disorder, right? So delta G, Gibbs free energy, takes into account all of the heat and all of the entropy or disorder and the temperature, and it tells us whether reactions are going to be spontaneous or not. Another way that we can calculate delta G, and this is only at standard conditions, is this formula that you have hopefully seen before when you were calculating delta S's or delta H values, right? So we have our change in Gibbs free energy at standard conditions equals the sum of all of the information about the products minus the sum of all of the information about the reactants. Okay, and that information includes N, which is the number of moles, times this GF naught value, which naught is standard conditions, and GF is the Gibbs free energy of formation. So we're looking at how all of the products are formed and how all of the reactants are formed. And I'll talk a little bit about that in a little bit. And then the third way we can calculate is using coupling reactions. So if we figure out how different things are produced, then we can add reactions together. And this is just like Hess's law. So if we add reactions together, we add the delta G values. Okay. And so since we just have one reaction, what I'm going to do is use the second equation to go through and calculate. Okay, so back to the question, is this reaction spontaneous? We're going to look at our delta G value and see if it's a positive or negative number to tell us if it's spontaneous. I have my chemical reaction here and the formula that I choose to use. Okay, so we have delta G naught equals the sum of the products minus the sum of the reactants. Now, I told you that these GF naught values are for, the little f stands for formation. And these are calculated for every single product and every single reactant we have based on the formation or the free energy change on the formation from the elements. So what I did is I found a thermodynamic table. It's usually in the appendix. In my book, it was Appendix 2. You can look on Wikipedia and find a thermodynamic table. And what I did is I went through and found every single reactant, and that includes the molecule and the state, so CH4 gas. And I looked up my G values, my delta G, it's sometimes called, or the G of formation. So what that tells me is this is the change in free energy that happens when this molecule is created from elements from the periodic table. Okay, so here we would take carbon as a solid, and usually that's graphite is the lowest energy state, plus 2 moles of hydrogen gas. Hydrogen is one of the Brinkelhoffs. In real life, it exists as H2, and it forms methane. Okay, so the delta G, or the free energy of that process, is negative 50.5. Now, oxygen, O2, is how we find, that's the lowest energy state, right? If I look at the periodic table and I see oxygen on there, when it exists in nature, it exists as O2. Because that's the way the element exists, the free energy, or GF value, is 0. Okay, and so same thing, like CO2 is created from carbon, usually graphite is the lowest energy state, plus oxygen gas goes to CO2, and that delta G value that's calculated from that process is negative 394.4 kilojoules. Okay, so like I said, I looked up these values on the table, and just make sure that your states and your molecules match exactly. Okay, so there's 2 different ways to kind of do this. The first way is I'm going to use this equation kind of write out. And then the second way is kind of my own special take on it. Okay, so first way is I take delta G, okay, and I start with the products. So what I'm going to do is put a big bracket and put all of the information about the products in this bracket. Okay, so the very first product I have is CO2, and I have 1 mole of CO2. So I have the moles, and I'm going to multiply that by the GF value. So I'm going to come up here, find my CO2. That value is negative 394.4 kilojoules per mole. Okay, and I multiply those together, right? So that's the very first one. Now this equation says the sum. So I'm going to add these next ones. So I have 2 moles of H2O, and I'm going to multiply that by my delta G value, or my G value for H2O. So that's negative 228.6 kilojoules per mole. I put a parenthesis, and my last one is ozone. So I'm going to add 4 moles of ozone multiplied by 163.2 kilojoules per mole. Now I'm going to end that bracket because I have gone through and done all of the products. Next, I'm going to subtract and do that process for the reactants. So I'm going to do this in purple, right? So subtract in purple, and my reactants will be in purple. So a big subtract sign. Then I'm going to take a big bracket and go through the reactants. So in my reaction, I have 1 mole of CH4. I'm going to multiply that by negative 50.5 kilojoules per mole. I'm doing the sum. So I'm adding these up, do another parenthesis. I have 8 moles of oxygen, and I'm going to multiply that by 0 kilojoules per mole. That's my last reactant. So I'm going to make and do a close bracket. Okay, so now when you're doing this, right, you take 1 mole of CO2 times negative 394 kilojoules. The moles are going to cancel out, and you're left with kilojoules. Okay, so make sure you do your orders of operation. So moles cancel when you multiply, and you're left with kilojoules. Moles cancel, and you're left with kilojoules. When I add those numbers together, the delta G value is negative 198.8 kilojoules. Okay, next I'm going to subtract. I'm going to do the same process for my reactant. So I take 1 mole, multiply by the G value, and I get negative 50.5. Moles cancel with moles. Kilojoules, when I multiply that, that's a 0. So this number right here is negative 50.5 kilojoules. Okay, so I take negative 198. It will go back to blue. Negative 198.8 kilojoules minus a negative 50.5. And the answer that I end with is a negative 148.3 kilojoules. So there's the delta G naught for the reaction. Okay, because it's negative, that means the reaction is spontaneous. So is this reaction spontaneous? Yes, delta G is negative. Okay, so negative delta G means spontaneous. That means if I mix methane and oxygen together, this reaction is going to happen without any external input. Okay, so we've gone through and we've used this equation. Now I want to show you a way that I do it to help me kind of keep track of everything that's going on. Okay, now what I do is I create a table. So I write my reaction down and I do this part, the moles times the delta GF in a table. Okay, so what I'm going to do is write over here the number of moles. Okay, and so here I have 1 mole of CH4 and I have 8 moles of oxygen, right? And I'm just getting that number from the coefficient. And maybe I'll write this in 2 different colors so you guys can see that I do the same thing for the products. Okay, so I have 1 mole of CO2, I have 2 moles of H2O, and I have 4 moles of ozone. So I've gone through and I've written down my number of moles. Next, I'm going to write my GF values. Okay, and that's going to go just underneath. And so for the first one, let's get my blue pen out. So CH4, I look up here and it's negative 50.5 kilojoules per mole. Oxygen is 0 kilojoules per mole. And then I go on to my products. For CO2, I have negative 394.4 kilojoules per mole. H2O, I have negative 228.6 kilojoules per mole. And for ozone, I have 163.2 kilojoules per mole. Okay, so I've written my number of moles, I've written my GF values for both the products and the reactants. Next, what I have to do is multiply. So I'm going to go and multiply these together, the top and the bottom. So 1 mole times negative 50.5 gives me negative 50.5 kilojoules. 8 moles times 0 kilojoules per mole, the moles cancel, and I have 0 kilojoules. Okay, so same thing over here. I'm going to multiply these numbers. 1 mole times negative 194.4 kilojoules per mole. My moles cancel, and I have 394.4 kilojoules. 2 moles times negative 228.6 kilojoules per mole is negative 457.2 kilojoules. Moles cancel. And the last one, 4 times 163 is 652.8 kilojoules. Okay, so I've gone through and multiplied those all together. So this multiplication step is done. Okay, and it's all in a table. So I've done this whole step in my table. Next, I'm going to take and do the sum. So I'm going to take and add these together. That gives me 50.5 kilojoules. And I'm going to take and add my products together, right? Because it says sum right there. When I add these together, I get a value of negative 198.8 kilojoules. Okay. Now, the very, very last step of this is we want to calculate that delta G value. Okay. And to do that, I'm going to do products minus reactants. Okay, so my products is this orange value. Let's go back to orange. So that's going to equal negative 198.8 kilojoules. We have a minus sign in there, so we put subtract and then my reactants. And those reactants is negative 50.5 kilojoules. So if I take negative 198.8 kilojoules and I subtract a negative 50.5 kilojoules, then my delta G value is going to equal negative 148.3 kilojoules. Okay, so is this reaction spontaneous? Yes, because my delta G is negative. So this process, making the table, helps me keep track of all of the little steps, keeps my orders of operation in order. And then I just have to remember the products minus the reactants part. Okay, so either way you do this, right, as long as you kind of keep it straight, then you'll be successful. So if you have any questions, please feel free to leave them in the comment section. Or if you like this video, like, share, and let me know other videos you want to see.